We are Group F701. Our project is about our tour with SKAPS Industries. Our group members are Tyler White, Colby Chauvin, Andrew Winkler, Zane Caudle, Kate Espy, David Bolt, and Cody Chandler. SKAPS Industries is a global manufacturer in geosynthetics and technical textiles. They're headquartered in Athens, Georgia, with 13 additional manufacturing facilities worldwide. Their products support civil engineering, environmental protection, and construction projects. Their focus is on durability, stability, and performance in challenging environments. This presentation will take you through the manufacturing process of SKAPS geosynthetic materials. These materials will go through the hopper, willow carding, carding machine, cross-lapping machine, tacker looms, roll drafter, second loom, roll stretch, and then finally the tenor frame.
Fiber preparation at SKAPS starts with the hopper system, which is the entry point for all the polyester or propylene staple fibers. A hopper's main job is to break up the incoming material and feed it into the line evenly. This step is important because consistent distribution prevents clumping and helps ensure uniform quality later in the process. From there, the fibers move into the willow carding machine. This machine further loosens and separates fiber bundles, catching any clumps the hopper didn't break up. It also begins the initial alignment of fibers. Together, these two machines prepare the material so the carding and cross-lapping stages can form a smooth, consistent web. After the fibers are clean and open, they move into the carding machine, which is where the actual web formation begins. Carding uses rotating cylinders with very fine wire teeth to comb and align the fibers into a thin, continuous sheet. This step is important because it gives the material its initial shape and makes sure the fibers are mostly oriented in the machine direction. Once that carded web is formed, it's transferred to the crosslapper. The crosslapper lays a thin sheet back and forth in alternating directions to build multiple layers. This layering increases thickness, balances strength in both directions, and improves overall durability. Slightly angling each layer also helps reinforce the final geotextile. By the end of this stage, we have a stable multi-layer web that's ready for bonding.
Once the geotextile has left the cross-lapping machine, it prepares for bonding in the tacker looms and roll drafter. The purpose of the tacker loom is to purposefully entangle the fibers of the textile, thereby increasing its strength. After the geotextile has left the tacker loom, it holds a more rigid shape and gains firmness. Then the geotextile enters the roll drafter, where the fabric is stretched and aligned. This is done for multiple reasons, such as ensuring a constant thickness throughout the fabric and removing any potential clumps or inconsistencies. From there, the fabric is moved to the primary tacking loom. This is the stage of production where the geotextile gains the most strength and durability. The primary tacking loom further entangles the fibers of the geotextile, though in a faster and more thorough fashion. The primary tacker has a higher needle density than the first tacker loom, and the fabric is punctured both on the top and the bottom of the fabric. This can be done in two ways, with the first being simultaneous tacking of the fabric from both the top and the bottom, and the second being through two different tackers that puncture the fabric from the top and the bottom independently. After that, the newly strengthened fabric enters the roll stretching machine, where it is again stretched to even out stress in the fabric and improve stability. This is done to ensure that the fabric keeps its shape as it nears the end of the production process.
The heat setting is the final step in the manufacturing process. This is where the machine holds fabric edges and stretches them along a heated frame. The heat setting also locks fibers in place to a fixed width and stabilizes dimensions. The operator can also modify fabric width to any customer's demands.
This location of SKAPS has production lines by DLO and NSE. The NSE lines have the enhanced ability for special needling patterns, but are often less reliable than the DLO ones. Newer lines have separate top and bottom needling steps, which has no effect on material properties, but controls fiber orientation. Additionally, the newest production line has a pilot prevention system during the dismount of completed geotextile rolls to ensure the textile does not get stuck and stall the line, which had been an issue in older lines.
SKAPS uses a few different types of resin in their product, largely based on the physical characteristics, mainly the increased ductility, chemical resistance, and flexibility. These resins will be run through the manufacturing process starting in the hopper system, willow carding machine, crosslapper, drafter, rollers, and ending in the tent frame. Their products are used in roads, drainage and landfills, erosion control, and can also be used to replace large quantities of concrete in some cases. When the product reaches the end of its life, it is often disposed of in landfills or incinerated. The Athens location focuses on producing non-woven needle punch geotextiles and produces roughly 40,000 tons per year, supplying over 60 countries. SKAPS can customize these geotextiles to meet certain specifications for tensile strength, water flow, and puncture resistance at the request of the customer. Other SKAPS plants focus more on geoplastics and erosion prevention bags.
Product data. The product data comes straight from the SKAPS website, which has things like strength and elongation. The GT is for geotextile, while the number following is for the thickness in mils, which is not millimeters, but an American unit equivalent to 0.001 inches. Now on to class connections. SKAPS uses rolling for uniform distribution. Uniform distribution lowers defects and potential failure points by making sure adequate material is in all areas. SKAPS also uses heat work to improve ductility, but this also comes with the added effect of lowering tensile strength. SKAPS tries to combat the loss of strength with needle punching, resulting in interlocking and stronger material. Here are our references. And now we have time for any questions.